Hi, welcome to the first video for lesson 4.4, which is going to look at bivariate distributions of the continuous type. Now, so far, chapter 4 is focused towards distributions of two discrete random variables, but now we're going to turn our attention to continuous random variables. So in this lesson, we're going to extend the ideas that we developed for bivariate distributions of the discrete type to the continuous case. And as was true with univariate distributions, the definitions are really going to be the same, except that instead of using summations like we did with discrete random variables, we're going to need to use integration when we're working with continuous random variables. So an example to kind of motivate us, where we can be looking at distributions of two continuous random variables, x and y. Suppose that the time at which train X arrives at Grand Central Station is uniformly distributed between 11:55 a.m. and 12:05 p.m. And also suppose that the time that train Y departs from Grand Central Station is uniformly distributed between 12 and 12:06 p.m. And suppose that the arrival time of train X and the departure time of train Y are independent. Then we can use a continuous bivariate distribution to answer questions like, what is the probability that a passenger arriving on train X will arrive at the station after train Y has departed? So we define our random variables here. X can be the number of minutes after 11:55 a.m. that the train X arrives. And we can see that X is going to be uniformly distributed between 0 minutes after 11:55 and 10 minutes after 11:55. We can also define Y to be the number of minutes after 11:55 that train Y departs from Grand Central Station. And Y is going to be between 5 minutes after 11:55 and 11 minutes after 55. So this is my uniform distribution. And we can see here that our sample space is going to be an area, a region in the XY plane when we're working with continuous random variables. Now, when we talked about joint distribution functions for discrete random variables, we called them probability mass functions. When we're working with continuous random variables, we don't call them that. We call them joint probability density functions, and so those would be called joint PDFs. A joint PDF is an integrable function, little f of x and y, of two continuous random variables, x and y, that satisfies these conditions. First of all, f of xy has to be greater than or equal to 0 for all values of x and y. And the support of x and y is the set of all the xy pairs for which this function, f of xy, is greater than 0. If we integrate over the entire support of x and y, then the total volume really under this surface is going to be 1. And if we want to find the probability of an event A, which is an area, a region of the xy plane, we can integrate over that region A, our distribution function, and that's going to give us our probability. So our joint probability density function is shown here as this sort of surface. And if we want to find the probability that xy is in region A, it's going to be determined by the volume over the region A, but under this f of xy surface. So similar to how we were finding areas under the curve to represent probabilities in the univariate continuous case, we are finding volumes under a surface when we are working with a bivariate distribution. Excuse my dogs. Okay, puppy crisis averted. Let's see, moving on. Let's try this. So because we have independent random variables here, our joint probability density function is going to be uniform over this region. And since the total area under the surface but over the region has to be 1, and our area of this region is 60, I know that f of xy needs to be 1 over 60. And this is defined on the region where x is greater than 0 but less than 10, and y is greater than or equal to 5 but less than or equal to 11. Now, if I want to know what is the probability that a passenger arriving on train X will arrive at the station after train Y has departed, what I'm really asking is, what's the probability that X is greater than Y? So take a minute and try to set up the integral that you can use to answer this question. Okay, so your integral should look something like this. We're going to take our PDF, 1 over 60, and we're going to integrate over the area that corresponds to the event that x is greater than y. Now, we know that y has to take on values of at least 5 and has to take on values only that are up to x because x is greater than y. So my limits when I integrate with respect to y are going to go from 5 to x. And then we know that in order for x to be greater than y, the smallest that x could possibly be is 5, and the largest it can be is 10. So those are our limits when we integrate with respect to x. So if I go through, I do my first integration. Now I'm going to integrate with respect to x and evaluate. I get a probability of 25 over 120. Now I can check this just using sort of basic math because really what I have here is this area is sort of a triangular box. And the base of the box is a triangle with a 5 by 5 kind of triangle. So the area of that triangle is 25 over 2, and the height of the box is 1 over 60, so I can kind of double check. I say, oh yeah, this makes sense. I got 25 over 120. Okay, so this shows us a little example of sort of how we can start working with joint probability density functions to calculate probabilities. In the next video that I'm going to make, we are going to start looking at marginal distributions and how to calculate means and variances of those marginal distributions. Then we will look at conditional distributions and how to calculate means and variances of those conditional distributions. Thanks, I'll see you at the next video.